Hi guys, in this video I'm going to go through the exam 1 review questions and I'm just going to go ahead and go through them one by one. So this is question number 1. I've got 4 different compounds listed here and I'm asking, are they ionic or molecular, type of bond, name. So to figure out ionic or molecular, what you're going to do is you're going to look at the two all the atoms that are in the compound and identify whether they are metals or nonmetals. You're going to be using a periodic table. Let me grab mine. You should know by now how to identify a metal versus a nonmetal. So silicon is a nonmetal to the right of the zigzag line, as is oxygen, and therefore this is a molecular compound, and it would contain a covalent bond. When you name molecular compounds, remember you use prefixes. So you just prefix of the first, prefix of the second. So there's one silicon. That would usually be mono, but mono is omitted on the first element if it's used on the first element. So you would just say silicon, di, and then oxygen, but you always end molecular compounds in "ide." No exceptions. If it's molecular, it ends in "ide." So silicon dioxide. Moving on to the second one, we've got another nonmetal in sulfur, and fluorine, also a nonmetal. So 2 nonmetals, O is molecular, O is covalent bonding, sharing of electrons, and once again, prefixes, omitting mono on the first. So this would be sulfur, and then the prefix for 6, hexa, and then fluorine, but make it end in "ide," sulfur hexafluoride. Copper and iodine. Copper is a metal. Iodine is a nonmetal, so therefore this is an ionic compound, held together obviously by ionic bonds, which are just the attractions of the cations to the anions. The metal is going to provide you your cation, the nonmetal is going to provide you your anion. The only time that you won't see a metal but it's ionic is if it contains ammonium ion. It's not a metal, but it is a cation. So that's the one time there won't be a metal, but it is still an ionic compound. For these, when it comes to the naming, always take a little look to see if your metal is a transition metal, and it is, Tm. It's a transition metal because copper is in this section of the periodic table, right there in the middle. With the exception of zinc and silver, which are always the same charge. So zinc is always 2+, silver is always 1+. All the other ones, I'm going to have you, well, not just me, but you're supposed to write the Roman numeral indicating the charge on the copper. I can tell that this is the copper 1+ cation because it only needed 1 iodine. And iodine is 1-. So if they're the same, if you have 1 of each, that means the magnitude must have been the same. Copper 1 iodide. So monoatomic anion, so you do change them to also end in "ide." This one says hexafluoride. That's kind of messy, but. All right, now this one here is magnesium's a metal. This is a polyatomic ion, which is just a collection of nonmetals. But therefore, you've got a metal and nonmetal, so it's ionic bonding. And it's not a transition metal, so therefore no Roman numeral. It would be wrong if you put a Roman numeral. Okay, you don't put a Roman numeral in the names of ionic compounds with with main group metals. So magnesium, and then you just name the anion, and in this case, it's a polyatomic ion. You do not mess with his name. That's phosphate. Notice you don't have any prefixes, no prefixes on ionic compounds. So that is number 1. All right, the next question, number 2. Is counting protons, neutrons, and electrons. We've got a few different ways of writing isotopes here. All of which are used. So this is number of protons, number of neutrons, number of electrons. So these two are pretty similar. Whenever you have the dash, remember this number right here is the mass number, which is the total number of protons plus neutrons. This, of course, is just a symbol. This is the word, but these are very similar. And then this is another type of way of writing an isotope, in which case you have the atomic number down there, the mass number up here, and this one happens to be charged. If you don't see that they're charged, that means they're not charged. They're just neutral. Okay, so unless someone tells you a charge, it's just assumed to be neutral. But this one is showing you that it is the 2+ cation. Okay, number of protons is very easy. Magnesium, periodic table, always has 12 protons. That's the atomic number. Let's just finish magnesium first. So this is the isotope, the form of magnesium that has a mass number of 22. So this is your mass number. It's the number of protons plus neutrons. So if you want to figure out the neutrons, you would just take the mass number and subtract out the protons. And that would give you 10 neutrons. Because this is the total of protons plus neutrons. Okay, so that must be 10 neutrons. Electrons would just be the same as the protons unless you are told to charge. That's what makes it neutral, to have the same number of positive particles as you have negative particles. Gold 195. Gold, you have to know that it's AU. You got to know that really quick. AU is atomic number 79. So that means it has 79 protons. To figure out the neutrons, you're going to take the mass number and subtract the protons. And that is 116. And the protons will match the electrons unless you are charged, and this is not charged. This one here, nickel. So that's the atomic number, which you either can just remember that or look it up on your periodic table. Nickel is atomic number 28. That means nickel will always have 28 protons, always. That never changes for nickel. If it had a different number of protons, it would no longer be nickel. It would be somebody else. So that's 28. To get the number of neutrons, when you have it written like this is the mass number. You can kind of think of it like this. This is going to be the number of neutrons. 58 minus 28, so that's going to be 30. And the number of electrons, how I do it is, if you have a 2+ charge, that means your number of protons, you have more of them than you have electrons. That's how I always think about it. If you are positively charged, you have more protons than electrons. And that will tell you how many more, like the deficit. You have 2 more protons than you have electrons. So that means you must have 26 electrons. Because 28 protons and 26 electrons will give you a 2+ charge. Okay, so that's how you would figure out the number of electrons from a charged particle. Now that's a positively charged particle. If it was a negatively charged particle, that means the number of electrons outweigh the number of protons. So you would have extra electrons, and you would have to add however many you need to get that charge. Number 3. How many non-metal atoms are there in a calcium chlorate formula unit? Calcium chlorate is an ionic compound because you've got a metal and a polyatomic ion. You, at this point, should just know that this is that species, chlorate, ClO3-. He's one of the polyatomic ions that we were supposed to have memorized several weeks back. Calcium is obviously the charged form of calcium because it's with an anion, so therefore it must be the cation or the ionic form of calcium. Calcium is in group 2, which means it always forms a 2+ cation. So there's your 2 species in this ionic compound, and it's all about how many of each do you need to get neutral. You would need 2 of these guys, because this only gives you a 1- charge, so you would need you would need 2 of them to get 2 negative charges to balance out that. So the formula is this. You would need 2 chlorates. Okay, that's what that 2 means. You have 2 chlorate ions for every 1 calcium ion. You need to think of this as a chunk, okay? It's not like the negative only applies to the O. The negative is the charge on the whole molecule, okay? It's literally, a polyatomic ion is literally a molecule with a charge. And in this case, it's a 1 minus charge. It's chlorine with 3 oxygen atoms, has a 1 minus charge. You would need 2 copies of that to balance out one of the calcium ions. So how many nonmetal atoms are there? Well, if you count atoms in here, you have 1 calcium ion, sorry, 1 calcium, it is an ion, but think of it just as atoms for now. That's 1 calcium atom. How many, but that's a metal. How many chlorine atoms do you have? Well, you have 2 chlorine atoms because you have 2 copies of this. So picture this twice. You have 2 chlorines and you have 6 oxygens. And those are both nonmetals. And therefore, let me give you a little therefore, you have 8 nonmetal atoms total. And that would be the answer there. Convert 1.47 picograms to milligrams. All right, this is just a metric conversion. If you never did the online lab that applied to this, which by the way is going to be graded, you know, when you come in for the conductivity lab, I think I wrote that in the announcement on it. You should have done that already. So everybody should have already done this. So this should be review. 1.47 picograms. And we are converting that to milligrams. For all of my metric conversions, I always use dimensional analysis. So, and if I'm going from one prefix, pico, to a different prefix, milli, I always go home first. I always turn it into plain old grams first. So in every 1 gram, there are 10 to the 12 picograms. I have that memorized. 10 to the 12 always goes with pico. 10 to the 12 always goes with pico. And as we talked about in that video, I always write it from the point of view of having in one of the base unit, or you know, the larger unit, have how many of the little guys are in there. It's going to be a positive exponent, okay? If you've trained yourself to do it the other way, where you're saying that 1 picogram, which would go on the bottom, is 10 to the negative 12th grams, which is also a true conversion factor, you can do that. You will get the same answer. But this is just how I do it. There are 10 to the 12 picograms. They're very small in 1 gram. That will cancel out picograms. And then we need to convert grams to milligrams. So in every 1 gram, there are 1,000 milligrams. And I wrote the gram on the bottom because I'm trying to get rid of it. I'm trying to get rid of it and turn it into milligrams. So I always go like, if you're going from one prefix to a different prefix, I always kind of go home first and then go to the new prefix. So see what I did? You go like kind of to the base unit first. It just makes it a little bit easier rather than trying to relate picograms to milligrams in a single conversion factor. You can do it. It's just not how I do it. So but it's fine. If you get the right answer, it works fine. So I just put in 1.47. Now I divide by 10 to the 12th. And then I press enter, and then I times by 1,000 because that's on the top. And I got a really tiny number, and I'll just use my calculator to do the scientific notation for me. And I'm getting 1.47 times 10 to the negative 9 milligrams. Okay, and that is the answer of that metric conversion. Moving on to the next question. Which element has the greatest molar mass? So we have hydrogen, oxygen. Notice I'm giving you the words here. Iodine, cesium, and barium. Okay, so you see the word, which element has the greatest molar mass? The key to this question is that you remember that there were 7 diatomic elements. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Which means that when you use the term hydrogen, okay, it's not in a compound. It's not like, you know, any dihydrogen monoxide or anything like that. It's just hydrogen. That's the element hydrogen. You have to remember that his formula is H2. Oxygen is also a diatomic. Iodine is also a diatomic. Cesium and barium are not. Cesium and barium are just, the vast majority of them are just atomic elements. So you would just, these are just single atoms. You should have all of these memorized. They are all on your list. So now getting their molar masses, you're just going to the periodic table. So for H2, that's 2 hydrogen atoms. So you would have to take 1.008 and times it by 2. There's 2 of them. So his would be 2.016 grams per mole. That's his molar mass. Oxygen, his molar mass would be 32 grams per mole. Now, I wrote it like horizontally like this, but as you know, I won't do 0.00, it's just 32. It's the same. I almost always write my molar masses like this because that's how you end up using them when you're doing your dimensional analysis math problems, like conversion factors. So that's how I usually write them. I2 is iodine, 126.9, but there's 2 atoms in it. So you would get the 253.8 grams per mole. Cesium would have been 132.9. I'll just kind of skip the unit for now. And barium, 137.33. So iodine is the winner. He's the heaviest molar mass. Okay, moving on to the next question. Question number 5. What is the mass of 1.794 times 10 to the 24th lead atoms? Now, that is the number in the question. Notice, every number has a unit. You have to attach the unit to the number. You can't just drop it. If you just write the number, you will not know what to do with the number. Okay, the unit is your best friend in the world because it's going to allow you to figure out how to do the problem. So it's that many lead atoms, okay? And we're trying to find the mass, which means grams. So I need to essentially convert this unit atoms to number of grams. And the key here is that really you have to just kind of be so used to this type of problem that you already can see how to do it, the pathway, how to get from atoms to grams. In chemistry, if you need grams, just get moles, because then all you have to do is a mole to gram conversion, okay? And that uses molar mass. Remember this little thing in one of my lecture videos. Now that is also how you're going to go from grams to moles, but you just use it, you know, the opposite way. But we're not in moles yet, so we're actually going to have to do something first. We're going to have to do this type of deal, number of atoms to moles. Okay? Remember, for that, you want to use Avogadro's number as a conversion factor. Now, you also use that going the other way, just the conversion factor flipped. But that's really how we're going to get it. If you can get it from atoms to moles to grams, then you can get the right answer. Those are the connecting points. It's like building a, I don't even know how to say, it's like building a railroad. Okay, you're trying to just connect this to that. So now it's just about writing true conversion factors, writing ones that actually are real. And a conversion factor, the whole point is the numerator and the denominator have the same value. Okay, they represent the same amount of stuff or measurement, whatever. So how would you write it like this? Well, you would say in every 1 mole, there are 6.022 times 10 to the 23rd atoms. That is a true statement, which is why you can use it as a conversion factor. Notice I take the time to write the word atom. I want, you know why? Because I want to make sure I set it up right. If you accidentally, you know, put the 6.022 on top, you'll see that the atoms don't cancel. So the whole point is to basically let the units tell you what to do with the number. So atoms is going to cancel. That gets you into moles. And now all we need is the molar mass of lead. And that, you go to your periodic table, you find lead. It's 207.2 grams per mole. And I'm going to write it in this orientation because I want the grams on top and mole on the bottom because mole needs to cancel. And that, oops, I wrote that wrong. 207.2 grams. That's the right number. And then you just have it all set up. Gram is the surviving unit, which is what you want. And you just plug it into your calculator. Now, 1.794. I'm using the second log function to get times 10 to the 24. When I enter that in, I just press enter. Let your calculator accept the number. Oops. Let your calculator accept the number, 1.794 times 10 to the 24. Now you're dividing by this number, but anytime you divide by Avogadro's number, you have to enclose it in parentheses in your calculator. All right, the whole thing has to get enclosed. So 6.022 times 10 to the 23rd, and I do that part, and I've pressed enter, and then you times that by 207.2. And that will get you the right answer. Make sure that if it's giving it to you in scientific notation, because maybe you had your calculator in scientific notation, make sure you do second DRG and make sure it's in flow. Press enter. You want it in flow. I got an answer of 612.264 and a few more decimal places, but the issue is how many sig figs to present in your answer. This number here had 4 sig figs. Okay, your original measurement had 4. Avogadro's number always has 4, and actually this one has 4. So your answer will be limited by whatever one is the fewest, in this case 4, 612.3 grams. That 6 will bump up that other 2 up to 3, and that would be the answer to this question. I just looked at it and it says 617.3. So I have a mistake. Let me track down my mistake. 1.794. Did I get the molar mass written for lead correct? 207.2. So let me just check. Oh, no, I'm just being goofy. I do have 617.3. I don't know what's wrong with me. I just read it wrong. 617.3. My bad. Yeah, I was just being sloppy. Okay, 617.3 is the right answer. Okay, the next part here. Number 5. Says a 20-gram sample, okay, you've got 20 grams of an element contains 4.95 times 10 to the 23rd atoms. Now we don't know what type of element it is. It just says of an element. Identify the element. So this is a classic, and I said this could be a good extra credit question because we hadn't done one of these in the lecture, and I don't know that there is one in the textbook that I assigned like this, but it's still a really good question. One of the classic type of questions in chemistry is identify the element questions, where you can just figure out the molar mass of it and then use the molar mass as a clue to what the element is, because the molar masses are all listed on the periodic table. So this is kind of a like construct the molar mass question. And construct the molar mass. Understand that the molar mass is the number of grams per mole. It's the number of grams per mole. So if you can figure out this number of the sample, and you can figure out this number of the sample, you just smush them together in your calculator, do the grams divided by the moles, you will find the molar mass. You'll get the molar mass. So in these types of questions, you're usually giving one of them directly and the other one you have to work for a little bit. The 20 grams is the mass of this sample. Okay, it's just been given to us. The 20 grams is the mass of the sample. If we can just find out how many moles are in there, we will get the grams per mole, which is the molar mass. So that's what that number is for. It's there to help us figure out the number of moles. And just like before, in every 1 mole, there's 6.022 times 10 to the 23rd atoms. Notice what I'm doing. I'm not taking any shortcuts with the writing. Okay, you will not. It's not wise to not write your units. It's actually very unwise. Good chemists will always do that. They're not so smart that they skip the units. It's not at all the right way to think about it. So you want to let those units cancel. And notice I've been doing this for years. I still cross them out, okay? You want to see them cancel, and you want to see the surviving unit survive. So now do 4.95 times 10 to the 23rd. You'll start with the left and just do whatever the sentence is telling you to do. So you do him, and then we are dividing by this because it's on the bottom. So I'm entering it, and then I'm dividing by Avogadro's number, remembering to put it in parentheses. I'm getting 0.82. Now, I get a huge number, well, with a lot of decimal places. Don't round too much, but you also don't have to be crazy. Keep maybe 3 or 4 decimal places. That will minimize any rounding error in subsequent steps, but it doesn't, you know, you don't have to write every single digit. So I'm going to write 0.82. Let me just write 199. And that's the number of moles. That's the number that would go down here. And now, if you put these two numbers in your calculator, you'll get the grams per mole. Actually, here's another thing. This is still in my calculator, okay? If I just now type in, so it's in my calculator, I just type in 20, whoops, 20. You don't have to do 20.0. The calculator doesn't care about sig figs. So 20 divided by, if I do second, and then down here, you see ANS, answer. That will basically use whatever the previous number was, and it keeps all of them in there. So then you really don't have to worry about rounding error at all. I'm getting 24.33 as a final answer. And the unit would be grams per mole, which is the unit for molar mass. And if you look on your periodic table, it doesn't have to be perfect because these are measured values, and if you know, it could be ever so slightly off, but hopefully you see that this element must be magnesium. And that is the answer. So this is kind of like a mystery element type question. What you want to do is construct the molar mass with the data that's given. All right, moving on, pressing on. Question number 6. What is the mass percent of nitrogen in nitric acid? So you need to know nitric acid's formula. So we'll just do that part first. To get a mass percent, you're just counting how many nitrogens there are. There's one of them. Then you put in nitrogen's molar mass. Then you put in the molar mass of the whole compound. So I'm going to have to add up hydrogen, so that's 1.008, plus a nitrogen, which is 14.01. Notice I'm doing this all in one calculator entry, plus 3 oxygens. Now you can do that in your head. It's the number 16 exactly. So you can do 3 times 16 is 48. Or if you don't feel comfortable doing that, just do parentheses, 3 times 16. And then the total is 63.018. That is how you would do the mass percent. So now let's go ahead and get that. I'm getting 22.23%. And I picked 4 sig figs because that's an exact number. That's not a measurement. You're just literally counting how many nitrogens there are. But these all have 4 sig figs, so that's why my answer has 4 sig figs, 22.23%. And then it says in a 3.5 milligram sample, how many, what mass of nitrogen is present. So therefore, what you have to do is you just have to take 22.23% of this number. And percentages are per 100. So you're moving it 2 decimal places to the left. So 0.2223 times 3.5 milligrams. Notice you keep that unit in there because that's what your answer's unit is going to be in, milligram, because it doesn't cancel, so it's still there. So 0.2223 times 3.5, and this has 2 sig figs, so he limits this answer. So you always pick whatever one has fewer sig figs. So this has 2, this has 4. So 2 is fewer. I'm getting 0.78. That's as much, you know, that's as many sig figs that you could report in that answer, okay? So that's how you would do that. That's one example of a time where you don't really have to get rid of the metric prefix. You can just leave it. If the original thing was in milligrams, you can just leave your answer in milligrams. But if you had put it into grams, then your answer would be in grams. It's all the same mass, so I wouldn't mark it wrong. As long as it's correct, it's the same mass. Number 7, okay, a compound is found to contain 64.80% of carbon, 13.62% of hydrogen and 21.58% of oxygen by mass. Now, keep in mind, the way that these composition percent type questions is when they do these experiments to find out these percentages, they're just talking about the percent of carbon atoms, basically, or the percent of hydrogen atoms, percent of oxygen atoms. In other words, you're not going to, this whole concept of H2 being a diatomic element, it wasn't existing as a pure element at the beginning, so it's not how you think about it. It's just do H and O. It's not about diatomic elements in this context. Okay, so for this question, remember, you always just visualize a 100-gram sample. Okay, you just visualize a 100-gram sample. It doesn't matter that it wasn't. You can just visualize one, because this is the percentages for any massive sample, which means that if it's a 100-gram sample, these percentages are the amount of grams in 100 grams. And that's how I start these questions out. I literally turn the percentages into grams. And the goal here is to figure out the empirical formula. I think that's what the question says. What's the empirical formula? So it's going to be C something, H something, O something. By the way, how did I know it was in that order? It's basically for carbon, hydrogen, and oxygen containing compounds. It's always in the same order as glucose, C6H12O6. If you had messed up the order, though, that's not going to be a deal breaker, okay? Because you have to actually know a little bit of convention to have even known this. But I wouldn't mark it wrong if you had messed up the order. But you need to get the subscripts correct. And remember, these are the number of moles. You can think of them as the number of moles. In an empirical formula, you can think of it as the number of moles. So we need to get the moles of each. So we need everybody's molar mass. I'm writing the grams part on the bottom because I'm trying to convert to moles. Okay, grams cancels all the time. We're left with moles. So now we just need to plug these in correctly. .3955. I'm not going to round too much. I don't want to introduce much rounding error here, because that can kind of mess with getting it perfect at the end. Okay, I can round a little bit. Now, those are the number of moles. So now I actually transport them where they go. So this is 5.3955. This is 13.512. This is 1.3488. Next step is you need all of these to become whole numbers. So the way that you do that is at least fix one of them by dividing them all by the smallest number. That will guarantee that at least one of them is fixed. So, but you have to do the same, you have to divide by the smallest of the three numbers, because kind of like algebra, you have to do the same thing to all the people. So now the O becomes a 1, right? But I'll leave that like that. 5.3955 divided by this number is 4, pretty much very close to 4. And H, the 13.1, is very close to 10. And so that is the answer. Okay, C4H10O. All right. Remember, if it's not very close to a whole number, then you may have to do that last step, which I showed you in one of the videos, where you have to times all of them by like a 2 or a 3 or a 4 to get them to all be whole numbers. This one didn't require that, but in, I think, the chapter 3 lecture videos, I did an example that did. Okay, question number 8. A newly identified element X consists of 2 isotopes. So let me start writing this down. So isotope 1, isotope 2. I've given you the masses. Now these ones here, these masses are obviously from a mass spectrometer. They're very precise. If you don't round them, use them as is. If you're given these very precise masses, then you want to use them. I think in one of the videos, we just kind of estimated the masses based on the mass numbers, which is fine, but if you're given real numbers, use them, don't round them. Percent natural abundance, so basically if there's only 2 isotopes, the percentages would obviously add up to 100, so the 2 numbers will add up to 100, which, just so you know, means that I could have just given you this percent and would have expected you to figure out the other percent. So be ready for that. If I only give you 1%, one of the percentages, logic tells you that the other one makes up the rest of 100%, and it does. Okay, so atomic mass. So we are just trying to figure out the atomic mass. So this is just kind of a simple type of question. The atomic mass is going to equal the contribution from the first isotope plus the contribution of the second isotope. And to get their contributions, you take the percent natural abundance, make it a real number that you can use. A percentage is just that divided by 100. Percent means in 100. So 0.6037, and you're going to times that by the mass of that particular isotope, and that's AMUs. Notice, never do I drop a unit, okay? You just never drop them. It's a measurement, so the number and the unit are completely linked. And then the same thing, 0.3963 for the second isotope times his atomic mass. Or sorry, his mass for that isotopes. For that particular isotope, that's his mass. And then you just take it to your calculator. So 0.6037 times 279.98. I'm going to get that number. And then I'm just going to press plus. I'm going to add. I'm just going to put this in parentheses. 0.3963 times 282.02. I like to minimize the amount of writing that I need. I'm getting an answer of 280.79. AMU would be the survive. You added an AMU to an AMU, so the answer would still be an AMU. And that is the right answer, 280.79. And for atomic masses, usually I'll ask you to report 2 decimal places. The sig figs, that you actually can do it correctly by sig figs, but it's a little complicated because you have both multiplications and additions going on, so kind of 2 separate rules. So we'll just kind of make that a little easier by just asking for 2 decimal places in your final answer for atomic masses. And then the last thing is basically just a reminder. We talked about several different scientists and what they contributed to scientific knowledge. We mentioned Antoine Lavoisier. We mentioned Proust. We mentioned John Dalton. We mentioned J.J. Thomson. We mentioned Ernst Rutherford. I think those were the only ones that we mentioned in this, mostly I believe in chapter 2. So do you know what they did? What laws did they discover? What did they, what kind of things did they do? Have you memorized all the polyatomic ions, elements, acids, and bases? There, it's an open book test. You can have that next to you. You can, okay? However, if you're not very familiar with it, you'll be literally taking possibly 5 minutes of precious time, 10 minutes of precious time looking for things. And if you don't have them mostly memorized, it shows me that you haven't actually been working with them that much, because with all the questions that the chapter has, self-assessment quizzes and end of chapter questions and stuff, you really should actually be memorizing some of this even by osmosis. So you can have it next to you, but you really should know them quite well. Do you know your way around the periodic table? Periods, groups, group nicknames, metal versus nonmetals. Have you read through and learned all the material in your class notes? Okay, so you should have, and I'm going to be grading it, so I really hope you have, or else it's going to kill your grade. You should have taken notes on every one of those lecture videos. There's part 1 and part 2 for all 3 chapters. You should be reading through those, and all of it is fair game to show up on the test. And did you do all the end of the chapter problems that I recommended and all 3 self-assessment quizzes? Just listening to me do lecture videos is not going to be enough to get you an A or a B and probably even a C in the class. You have to put the work in to make yourself learn the material. And chemistry does take work. You have to work at it to learn it. So hopefully you have been doing that all the things that the textbook provides. I'm not giving you a whole lot of practice questions because I think it's completely unnecessary when you have an amazing resource in that textbook. They, you know, they're really good. If you do everything I'm telling you to do, you should learn the material. So, all right, good luck studying. Hope that was helpful. We'll see you, well, I guess, well, you know, take the test, do it online. Don't forget, it is timed, and it is given at the time that's on your syllabus. No exceptions unless you have worked out something with me. A few of you have, you know, different situations for this particular test or whatever, but everyone else, I am already expecting you to show up on time, okay? Good luck.